Okay, so hello everybody. Our speaker today is Klaus Liegener from Technical University of Munich. So maybe a short introduction. So Klaus finished his PhD in Erlangen under supervision of Thomas Liemann, and then he made postdoc in Louisiana and then also in Hamburg in Dresden. So he will talk today about semi-classical cosmology in loop quantum gravity. So Klaus, you're welcome.
Thank you, Wydział. Thanks for the nice introduction. And thank you for giving me the opportunity to talk here at the Warsaw Gravity Seminar. It's really a great chance for me. Yeah, so what I want to talk today about, I mean, it will be a talk about quantum gravity. So there will be a lot of quantum involved, but also general relativity. And since you have a big quantum gravity group, I think you know the basic motivation behind quantum gravity. We want to solve the breakdown of singularities of the GR. So I will skip this part of motivation because I think most of you have heard this already a lot of times. And instead of that, let me say, I think that there's a second part to this whole quantum gravity point. Namely, while we are trying to more and more come towards a theory of quantum gravity, these models, we are always developing some tools, some mathematical models which we can apply, which have hopefully even, which we hope to use to solve quantum gravity at some point, but which maybe also have application outside of quantum gravity. And I think this is a very important part because this is the output we as researchers present on top of some conjectured quantum gravity models. And my goal for today will be that I present two of these frameworks which we have developed in the last years, which are on a fairly general level, which have some applications for GR, for quantum theory in itself. And to showcase that they really are useful, I will in this talk apply them, of course, to quantum gravity, especially to quantum cosmology, to showcase what their strengths are and what they can do. And when I say quantum cosmology, of course, I want to give you just a brief overview what I mean coming from the loop field with quantum cosmology and where these methods will come in. So very briefly, loop quantum cosmology, this is the sort of canonical quantization of a polymerase version of isotropic Friedmann-Lemaitre or Robertson-Walker cosmology. So why cosmology? What is isotropic? This means, which characterizes cosmology, right? Isotropy is the invariance under a certain symmetry group, namely the invariance under spatial translations or rotations of our spatial slice. By the way, I will always work in the Hamiltonian framework with this talk. And if you have this spatial slice, you actually see there's only one degree of freedom left, a scale factor, right? It's A, and in the canonical framework, we are used with slightly different variables. So we denote P as A square, in which case you can get a symplectic structure, Poisson bracket of cosmology, dc dp, very standard like mechanics. And you can actually compute the evolution of cosmology totally classical. So this is sort of, if you go from GR to cosmology, you have a scalar constraint, which is proportional to square root of P and C square, where C is the momentum to P. And then you can go to the quantum theory. Of course, directly quantizing it gives sort of the Wheeler-DeWitt quantum theory, which is not so good. It doesn't really resolve the bounds to the Big Bang in the way we want. Therefore, a way to envision loop quantum cosmology is to polymerize the standard cosmology. How you do this, we will talk about in this talk, and it will give you a sort of new scalar constraint, which is polymerized. And if you quantize this theory, you get a physical Hilbert space with this polymerized constraint operator, which is the AQC Hilbert space, and you can really study the evolution of semiclassical states. Coherent state sharply peaked on a classical trajectory, and you will see that they resolve the bounds, which is a famous work by Ashtekar, Pavlovsky, and Singh. Of course, along this way, there are several points where you might be a bit skeptical of how this really happens. Like I told you, well, we introduced this polymerized cosmology, but how does this really relate to GR? What is the connection here, and in what sense makes the sense to consider such a polymerized constraint operator? And the other question, of course, is, well, this is the semi-classical limit of a quantum theory with only one degree of freedom. How does this relate to the quantum theory, to the semi-classical limit of a quantum theory of full GR? All of the things I will talk about today, I will not answer them in all generality, but I will make a bit way forward and present you tools how to solve this. So this was my motivation. I will split my talk more or less in two parts. The first one will be about this classical thing, which means how does this polymerized version, this easy system of just one degree of freedom, relate to the full GR. This is a problem called symmetry restriction, why this works in general. And then the second part, I will talk about the coherent states, and will show that they are proposal for our semi-classical quantum cosmology, and I will present a tool, the quantum speed limit, which can help us to determine whether it's a good tool or not, the coherent state. Now, then I conclude. All right, so let me get into the first part, the symmetry restriction. As I already said, we work in the Hamiltonian formulation of GR in this way. So if you are in a Hamiltonian formulation, you always have a phase space. And so forget about GR for a second. We just work with a phase space over some field theory. So M will be denoting our phase space. Omega will be a symplectic structure there. So a symplectic 2 form, which gives rise to a Poisson bracket. And since I told you cosmology is sort of related to an invariant subspace, invariant under symmetry group, I will talk also about a group now, namely a group I call phi, which will be some symplectomorphisms on our phase space. So they relate different physical configurations to each other. Once again, so okay, phi, this is a map from phase space to the phase space. You can do this not only with the physical configuration itself, but also with functions or like observables. And it's in symplectomorphism. What does this mean? This means that the symplectic structure is preserved under it. So action of our representation of our symplectomorphism phi on the symplectic structure leaves it invariant. Symplectic structure, like I said, is always closely related to the Poisson bracket via the Hamiltonian vector fields. Now, to avoid confusion from the onset, I talk about the phase space and symplectomorphism, which change one physical configuration to another one. This is something else than the physical spatial slide on which our theory lives, right? So sigma I denote by spatial slide, and there are some fields, for example, in GR, the metric field, which live here, but one configuration for such a whole field is one point in our phase space. So what you also have, and you think about this very often in GR, you have the typical spatial diffeomorphisms, for example, which change your phase space by moving one point, change your spatial slice, right? They move one point from the spatial slide to the other one. This is something else that is symplectomorphism I talk about here. Although there's of course a relation, right? If you imagine a translation which shifts all of your points in the spatial manifold in some direction, this relates also to a symplectomorphism in the phase space, moving you from one configuration to possibly another configuration. And if you think about this, you can very well imagine there might be some points in phase space which are invariant under such a symplectomorphism. Once again, the basic example being isotropic cosmology, where you have translations. They really move you in the spatial slice, but cosmology would be a point in phase space which is invariant under such a translation. So this is the invariant subspace, and it is really interesting. So I would call this invariant subspace M bar. M bars are all the points which are invariant under the action of the whole group. And like I said, cosmology would be an example, but I will talk about this later. In general, this invariant subspace has the property you can restrict functions or endforms to the subspace, right? It's simply evaluating your function only on this subset of points of the full phase space. And of course, if you can restrict your Poisson bracket, your symplectic form, then you can also restrict your Poisson bracket. So there's a natural way to define a restricted Poisson bracket from a symplectic structure. But of course, what is the relation of this restricted Poisson bracket to the full Poisson bracket? In general, if you would compute the evolution of an observable by a Poisson bracket with Hamiltonian, the Hamiltonian equation, this would be something else than if you would first restrict and then compute the evolution. Of course, very often it would be very nice to only compute the restricted system because it has typically less degrees of freedom. It would be great if you could go from a field theory, which is GR, to only the mechanical part of Robertson-Walker cosmology. But in which cases does this really work? When can you really analyze only the restricted system without losing any information, without doing any errors? Well, without giving you a proof, but we proved this recently together with Wydział from Warsaw. You can prove the following thing as well for finite dimensional, for the infinite dimensional phase spaces with certain conditions, that if you have such an invariant subspace and its restricted Poisson bracket from the full phase space with respect to your symmetry group, and moreover you have a function which is invariant h, for example Hamiltonian, then the flow which is generated by the restricted Hamiltonian with respect to the restricted Poisson bracket actually agrees with the flow of the full Hamiltonian and the full symplectic structure restricted on this invariant manifold. So in other words, if you evolve any observable with your Hamiltonian, yeah, when you evaluate this evolution on a point on M bar, so on a point which is invariant, then this is exactly the same as if you would first restrict your arbitrary observable and your invariant function h and compute it via the restricted Poisson bracket, really making it super easy to compute the evolution of a typically very complicated system. And I want, of course, to show you how to apply this, but before we do this, just very quickly, because we will talk about GR, GR, you know something. This is very typical for GR, it's a constraint, because GR is a totally constrained system. I've already talked about Hamiltonian so far. Apart from deparameterization, which you can also do, I want to talk quickly about the constraints itself. So, yeah, phi is not in general a constraint, the group of gauge transformations. There could be a separate group of gauge transformations, and their generators are the constraints. So I call them J. Of course, these gives rise to the constraint surface, J inverse naught, and then you can do something which is called symplectic reduction. You only look for those points in the phase space of your constraint surface which are modded out by action of your gauge group. Like I said, this gives you in nice situations, this gives you a manifold M/G, and you can also allow a reduction of the symplectic form to this manifold, symplectic reduction, and gives you in general a very hard phase space to work with, especially if you have a very complicated gauge group. But if you have functions which are invariant, then their flow will also preserve this constraint surface. So this is nice, but gives us typically a very hard symplectic phase space to work with, where we have the constraints implemented, which would be the nice thing. But I said this only works in nice situations, that is a manifold, and namely in those situations where there is not an invariant subspace for some part of my gauge group. If you have something like this, yeah, so if we consider gauge, which we consider a group, part of our gauge group, for which there exists such an invariant subspace, then typically you will have kinks in your resulting M/G. So this is not a manifold anymore, and makes this thing even much, much worse. The nice thing is that this framework of symmetry restriction I've just told you about serves as a complementary procedure to this symplectic reduction, especially in those points where the manifold description would break down. If you can really show this, if you first do your symmetry reduction to M bar, and then implement the remaining symplectic morphisms of your gauge group, then you can do your symplectic reduction with respect to them. And this really gives you the correct result, the correct dynamics and the correct behavior of these points, which would be singular in this typical symplectic reduction. Which is interesting in the case of GR once again, because GR, where our gauge group are the diffeomorphisms, of course, we know we have these invariant spaces by cosmology for translation, rotation. Okay, so now let me get really to the meat a bit and talk about GR in detail. So, like I already said, in GR, we are in a very special situation. We want to apply our framework of symmetry restriction. We know that our whole gauge group is the group of all diffeomorphisms on the spatial slide. Any diffeomorphism can be understood as a symplectic morphism in the phase space of GR. And I will use here the connection formulation of GR because later on we'll talk about the quantum gravity, which is based on Archdecke-Barbero variables. Which means I am sure you know this, but just to recall it quickly, you rewrite your spatial metric in terms of some electric fields, the E fields, and by rewriting it in this way, the connection, you introduce an additional gauge symmetry. Namely, you have this indices I, J going over the gauge group, internal indices. So a phase space which is completely equivalent to GR would be this phase space of the Archdecke-Barbero variable of the electric field and its associated connection, as long as the determinant is not zero. So, like you don't want the determinant of Q to vanish. On top of that, you have this gauge group. And actually, I really say here the gauge group O3. So people are familiar with Archdecke-Barbero for formulation, probably know the gauge group SO3. You can use really either ones. It's just the fact that you add the -1 as well. So it's not just a connected component, it's SO3, but O3 as well, because the action of -1 really gives you a new pair, which also transforms. So this thing also transforms like a connection and is still like a vector field. And this is the action of any SO3 part. So the G plus is just the component of the identity. And if you would incorporate the action of this gauge group on this phase space, you would restrict yourself to the phase space of Q and P of GR. All right. But now we want to lift the action of our diffeomorphisms to this Archdecke-Barbero phase space. And I told you always it's possible, but how do you do this precisely? Especially because we have added now this O3 gauge freedom. Clearly, there's a natural way how to implement the action of a diffeomorphism on vector fields and on forms. But how to do it if you have also this index of the gauge group, I index. In principle, we don't know how it should work. We have there a certain freedom. And we would like to show that this is possible. It's just a small fact aside, so you know it can be done. We just don't implement our diffeomorphisms as the action of the symplectomorphism on the phase space as purely the diffeomorphism, but also as a part which acts on this O3 index of the gauge group. Because if we tune this additional action in the correct way, we can ensure that the action of our lifted diffeomorphism really, if you go with a psi star and then add the O3 associated gauge transformation to it, it remains invariant. It cancels itself, which makes our life much easier. It's a choice. But with this choice, we have really an action of any diffeomorphism you ask for on our symplectic phase space. And now we can use this framework of symmetry restriction. Now we can really say, okay, let's give us a precise symmetry group and see whether we can simplify the O3 theory to a few degrees of freedom. If we want to do this for cosmology, so after W, we really talk about the translation and rotations. And the first thing we have to look at is, of course, the symplectic structure. So the first thing we will notice right away, and this is something which is, of course, already known in the literature, if you want to restrict also symmetry, symplectic reduction, your symplectic structure, which is the integral over the spatial slice, and the spatial slice would be non-compact, then you cannot really do this. Because our invariant subspace is parameterized by parameters, only P and only C. Right? This is really, this is the group of translations and rotations, like I said. And the only invariant subspace is, parameterized by these two parameters. Nice, because it would make computations very easy if you could work with a symplectic form, which is restricted, but restriction of the symplectic form, if you set a P here and a C here, no dependence on X, integral over a non-compact manifold would diverge. So this doesn't work. What we can do instead, we can restrict ourselves to a spatial slice, like which is compact, like a torus. Right, so we would introduce some length of the torus T. This is just a coordinate, and on this finite slice, could really restrict this. So we would get a finite number here, and then we would have dp wedge dc. Very simple symplectic form. And now our theory of symplectic symmetry restriction really tells us that if we also reduce the constraints, we can compute the flow of the constraints on this reduced phase space without losing information. Actually, you think now there are a lot of constraints. This is called hypersurface deformation algebra, vector constraints, scalar constraints with all different labs and shift functions. But as you can also show, the only constraints which remain and which we still need to implement are those where the labs function and the shift vector are invariant with respect to the action of the symmetry group. Now, very easy, since the group is all translation and rotations, there's only one scalar function which is invariant, can be the constant function, and there exists simply no invariant vector field, which is not trivial. So all the diffeomorphism constraints are automatically implemented, and there's only one scalar constraint which we need to reduce, namely the one smeared with the one function. You can restrict this very easily. If you write C in the Ashtek-Ribera variables, you restrict to C and P, you get C squared square root of P. Maybe you remember I wrote this down with motivation, and of course there's a matter part. This is really standard cosmology. So, well, we have not learned anything new, but we have seen this framework works. It gives us, in standard case, classical cosmology, but you could, of course, use this for any other system you're interested in, as long as you know the right symmetry group. So let's get fancy and see if we can use this also for situations which is more interested for quantum gravity. I already told you, well, one of these steps in between was this polymerization, where you would, instead of working with C, suddenly there's a sign C. Why should there a sign C appearing? Could we reclaim such a constraint as well, starting from something which is related to full GR? And in fact, you could. If you, instead of working with continuous GR over a continuous spatial slice, work with sort of lattice GR. So what do I do here?
Klaus, can you come back for to the previous slide for a moment? So I think you a bit oversimplified, because this SO3 is not working on the, it's not acting on the torus, yes? So you need to restrict a bit this group. You cannot assume that it's, you need to take it in the integer number, SO3 integer part, but it still works, it's still the same, yes? So the restriction is still fine, but you need to restrict a bit, yeah.
Thank you. Fair point. You restrict the rotations around 90 degrees, you can still do it. Yeah, and I think I write also the correct gauge group, symmetry group later on. Okay, so I wanted to tell you about lattice GR, where sort of taking the viewpoint of maybe if you would zoom in strongly enough, you would at some point don't end up with a continuous GR, but maybe you at some point see a discrete structure emerging. If you would take this viewpoint just for a second, of course, you can make this lattice finer and finer and finer, but there's a very fine lattice, some of parameterized by epsilon. Then you could restrict all of GR only to the excitations along the edges, the vertices of the lattice. So what we will do now is we'll take this phase space of GR and truncate it to this lattice. So we will work only with some degrees of freedom, which come from the connection and triad on the lattice. And of course, you will also change your gauge group. So for example, instead of the gauge group of 3, which acts on A and the guess will be a big E, the connection and the triad, you will also have a new gauge group which acts on the new degrees of freedom, which will be the holonomy and the flux. And we will make it in such a way that this diagram decommutes. So truncation of transform theory will leave the same. The gauge action here should lead to the same gauge action down here in the truncated theory. It's not possible for all constraints, but for the gauge constraint it works. So how does this truncated phase space look like? Well, it's an approximation to GR. So we work with holonomies, which is just the connection smeared over the length of our curve. And the flux is actually the gauge covariant flux. So this knows about the connection and the triad as well. So mainly it's the triad, but also knows a bit along the face where the edge where the triad lives on. And there's, I assume now, a dual cell complex which exists to our lattice. So you can smear with respect to the faces of the dual cell complex. If you have worked with architecture variables, you've probably seen this standard behavior from lattice gauge introducing holonomics. And this is now a kinematical approximation to GR, but you can also approximate the constraints by truncating them from the discrete from the continuum. But before I do this, quickly, what is our symplectic form of lattice GR? Well, it's also a truncation of the symplectic form of continuous GR, where it's just a sum over symplectic form on all edges, and on every edge, it's really that H and P are our canonical conjugated variables. This symplectic form looks such a way, omega is the Markov-Cartan form, and this really gives us that also the fluxes are non-commuting. So these gauge covariant fluxes, Pi and Pj, gives us a new Pk times the structure function of SU2. Why SU2? Because this is the lift SO3 to this discrete truncated theory. And now, like I said, we need also to truncate the constraints. So gauge constraint, for example, it's very easy. You can, like I said, we want to truncate the constraint in such a way that gauge transformations really commute. It's possible by introducing a gauge constraint, which is simply the sum of the gauge covariant fluxes. And this really gives us that diagram of the previous side commutes. This is not as easy with the other constraints, this diffuse and the scalar constraints. And namely, there is no way to really translate them directly. There's a way to truncate. So to introduce a new function, for example, the scalar constraint now, scalar function constraint CE, which is such that epsilon, which is the coarseness of our lattice, so to speak, the lattice spacing. If you send the lattice spacing to 0, this constraint becomes the continuum constraint. But as long as the lattice is finite, this constraint will be different than the continuum constraint. So I'll just flash this to you. I don't want to go into detail, just so you have seen that this function really exists. It's a very horrible looking expression. Basically, it splits into two parts. This is the regularization by TUM, where you split the Euclidean part and the Lorentzian part. Like I said, very long function, but it's completely written in terms of the holonomies and the fluxes of our lattice. You don't need to know the details in order to understand what happens now. Don't worry. So we want to get now a version of cosmology from this lattice GR. So once again, we work on the torus, and now I introduce this lattice spacing. I give it a concrete name. I call it mu0. This is simply just the length of the torus divided by the number of points. And for simplicity, I said t equal 1 in the following. And we have to think about the symmetry group. Once again, we have here the problem that we cannot really talk about all rotations, torus, and moreover, we cannot talk about all translations because we're on a lattice. So if you assume a cubic lattice, you can only move in steps of the lattice spacing. So our rotation group reduces to rotation around the cardinal axis, and translations are just the set of discrete translations. But if you would perform symmetry restriction with respect to this group, then you can really determine a set of points which are left invariant on our full phase space of lattice GR under this group, which is a symplectic morphism by this group. And these are all the points where the fluxes are parameterized by this number P, and the holonomies simply by this number C. And that's it. So it's again a space spanned by two parameters. You can reduce the symplectic structure by the version of symmetry restriction. You get DC, EP, DC. So the same symplectic structure like in the continuum, which is very nice. So you know you can compute the evolution of this horrible lattice GR, which have a lot of degrees of freedom, once again for the cosmological case by this same mechanical setup. But you also have to restrict these constraints. By a similar logic, only the scalar constraint with constant lab survives. And it looks differently now than it did in constraint case, the continuum case. Namely, you have really this sign C introduced. And also, because of derivation from TUM, there's a sign 2C here. And like I said, you can really compute now the evolution with respect to this constraint, which is the restriction of the full truncated constraint to the cosmological subspace. And you know that evolution produces is really the full evolution of the full lattice. If you do this, just to tell you, you get a bounce. It looks a bit different than if there were only a sign square. So this simple polymerization leads to a different result than the one if you restrict Tiemann in the correct way. But the main message I want to tell you is you get a bounce. So if you would have a scalar field here, free scalar field, this would be the evolution with respect to the scalar field clock. You get a bounce. And so, you know, this full lattice GR system, independent of how many lattice points you integrate, only this number mu0 knows about it. The more you write, of course, the more this one approaches C, and the more the bounce becomes at lower and lower volumes. But it will always be the correct dynamics. So I'll just wrap this part very briefly up before we go to the quantum part. This framework of symmetry restriction allows us really to work in the Hamiltonian framework, where it's typically not so easy to find symmetric solutions. But here we can really use this to kinematically reduce to a invariant subspace and know whether this invariant subspace, whether the evolution of some Hamiltonian or constraint will remain in this invariant subspace, and whether we can use the symplectic form on this invariant subspace in order to make computations much easier. A few comments to this tool. First of all, in applications, typically it's a challenge to find a suitable symmetry group. Like Wojtek pointed out, not all rotations work, then you have to restrict to only the cardinal rotations. Does your invariant subspace really reduce to the correct one under this symmetry group? In other situations, it might be even much more complicated. We have obtained a few insights on the gauge group along this way, which I briefly glossed over this, but you can really know that you can truncate your gauge group as SO3 or O3 to the right one. There's some funny thing happening if you consider very coarse lattices. If you consider a model which goes along full lattice, which is a sort of a large transformation of SU2, which still remains in this discrete structure, which is typically not seen if you only consider the constraint the space generated by the constraint. Also, for those experienced in the recent literature on loop quantum gravity and this gauge covariant fluxes, the process which we have done here really gives a correct procedure how to translate gauge covariant fluxes within invariant subspace, and really tells us that is again the symplectic structure of dpdc and this sign C with square root P without any additional modifications. So this is really the correct thing of how you should treat the gauge covariant fluxes instead of working with some postulation of them. Symmetry restriction is really a powerful tool. You can apply it to a lot of systems, and we have done many of them I won't talk about now, but you can also do K+, K- cosmologies, you can do Bianchi, you can do Bianchi 1 of the lattice, and probably there are many more applications waiting out there. An important message right now is, as you can see, you can get a bounce which happens slowly, solely due to discretization artifacts. So the fact that some of this whole GR on the lattice in Ashton-Gileo variables produces a bounce is not a genuine quantum prediction, but happens really in a classical discretized theory. So now the real interesting question will be, what happens on the quantum level? We should really understand this. Is there a way of talking about these invariant systems also on the quantum level? Can we know something about the dynamics as well? Because at the end, we want to find the quantum modifications for continuum system and not this discretization artifacts. This will be the part section now of my talk. But since we translate to the quantum, I think this would be a good moment to make a short break to find out whether you have some questions on this classical part first.
So maybe I will only tell some small comment that this nice modification of the bounds is from your paper with Andrea and Tomek. Yes, Pawłowski. I think Andrea Dapor and Tomek. Yes, so am I correct?
Yes.
Yes, so, and it was earlier, I think, than our paper. And the goal of our work was somehow justify this procedure that was done in this, to derive this constraint 28.
Exactly. The work with Pawlowski and Dapo and also Media Sanusi was on the quantum level, so where we really quantized again this, like I said, this reduced phase space and studied the evolution of a coherent state parameterized on this reduced phase space, right? So this is not a coherent state on full lattice GR, but only the small phase space, and you could see this one evolves, and the mean value follows this trajectory. Well, but the question is, of course, does the quantum state, which is only parameterized by one parameter, is this evolution somehow related to the phase space, to a coherent state which would live on full truncate, the full lattice? So a really complicated phase space driven by a much more complicated phase space. And this will be now what I want to talk about now, unless there's another question by Kedrick.
Hello, I have another comment. So one of your conclusions is that big bounce happens solely due to discretization. So I would agree with this statement partially, that discretization leads to big bounce. However, historically, that big bounce which you mean here was this first model where big bounce happened at some random values of energy density. But in the improved model, this big bounce happens in at some natural value of energy density, which is discretization independent. So I think that that big bounce which we describe in the so-called improved model is not just an artifact of discretization.
You're perfectly valid. Yes, I totally agree with you. Like you said it, right? Discretization leads to a bounce, which happens and leads to this bounce in the so-called mu-naught scheme, which is not related to the new bar scheme. Actually, there's, to my understanding, yet no concise way to relate or derive the new bar scheme somehow from a full theory perspective. But you're completely right. If you adapt the new bar scheme, then you would find this bounce happening at a very unique scale, which is independent of your discretization, sort of. The discretization parameter you introduced while going from the cosmological continuum theory to the improved dynamics theory. But like I said, our goal here is a bit to look at this relation to the full continuum thing, or at least to the full lattice here, which approximates the continuum much better than just 1 degree of freedom. Therefore, this talk will not talk so much about the new bar scheme, but really just about the findings in the mu-naught scheme, because this relates to the well, this allows at least this nice translation to lattice GR. Okay, so then I will talk about the quantum a bit. Just to set the stage a bit, I told you about this framework of symmetry restriction on the classical level, gives the possibility to reduce full general relativity in cosmology, but how to do this on the quantum level? I cannot answer this question completely, but I can at least give a bit of a direction which might be helpful. In this talk, I will briefly introduce the kinematic Hilbert space of full quantum gravity restricted to a lattice, where I will introduce coherent states. So these are semiclassical states of some classical configuration, completely kinematical, but we want to find out something about the dynamics. So what we did is we developed some tools which allows us to compute the expectation values of arbitrary polynomial operators, including their quantum corrections. So including somehow, if the spread is big, then state is not 100% coherent, not 100% peaked on the semiclassical trajectory. And this extra correction we can also estimate. And then I will introduce the quantum speed limit to do something useful with this ability to compute the expectation values and draw some information on the dynamical behavior of said coherent states. Let's get to it. So this will be now very basic for the people who have already know quantum gravity by heart, but just to streamline notations and don't do the others, I will briefly say everything. In lattice GR on every edge, except we have a holonomy, which is SU2 valued. So we are naturally interested in the Hilbert space of SU2 quantum theories, which is parameterized by functions over SU2 equipped with a Haar measure. That's the left and right invariant measure on the group SU2. If you have this space, you are very happy because you know there's the Peter-Weyl theorem, which lets us write every function on the space of spherical function in terms of the irreducible representations. So there's always some linear combination where dj and n labels our irreducible representations. So j is the representation which goes by 2j plus 1 up. And this dj, so these are of the functions that are like basis functions because they form the normal basis on our Hilbert space in the sense that they 1 over dj. They are orthogonal basis. If you take this dj, which is just a number, 2j plus 1, into these things as well, then they become orthonormal. So this is our basic framework by which we can write every function of, so every state of our quantum theory on one edge. One state which we look at is the coherent states. The complexifier coherent state is originally inspired by Hall and then written down for SU2 correctly by Thiemann and Winkler, who investigated the properties. So as you see, this is sort of a Gaussian because it has this minus j squared term, which exponentially fast decays, and then you have this basis function and this element h, which is a SU2 element, and labels the classical configuration, which our coherent state is peaked. So since SL2C, it's a bit not so nice, there's a okayish way to write it down, namely in terms of 2 SU2 matrices, and this exponential to the power of the Pauli matrix, so sigma 3 Pauli matrix, and this complex number xi and eta. This is a semi-classical state. This terminology semi-classical is very much fitting because the spread of the state is sort of labeled by the parameter t. If t becomes very, very narrow, then you find that the expectation value of an holonomy and the flux, remember these are basic variables, they are really peaked on sort of like the real part, quotation marks, of h, and this imaginary part eta. So this is sort of the flux part. This is the holonomy part of a classical holonomy, by which I write down my SL2C element. So the expectation value of these basic variables really gives me the classical holonomy and the classical flux, which with these basically holonomy is just a multiplication operator, and the flux operator is a right very effective field. But this is nice. So I know that I have a coherent state. Kinematically speaking, gives it to me for the basic variables the correct thing if I exclude corrections of order t. By the way, it should be a 1 because I have a 1 over t here, but same logic applies. There are higher corrections which you could also compute if you take the extra time, but if I ignore them, I get the classical correction back. And this was on one edge, but of course our lattice consists out of many, many edges. So I have to take the tensor product of all of these, and then I get a coherent state kinematically of the whole lattice. Since we will be interested mainly in cosmology, I will write this SL2C element at this n and n tilde in such a way that for my cubic lattice I have 3 directions and n being equal n tilde, only depending on the direction. 2, that should be n1, n2 should be written here, and n3 on the right side are certain SU2 elements, such a way that I get really classical holonomies of cosmology. And then C and eta would simply parameterize cosmology. So eta more or less proportional to P, which is our scale factor, and Xi is the associated momentum. And like I said, this would be our whole lattice state. And then we would be interested to evaluate the expectation values of our functions like the volume or the evolved volume or the scalar constraint or something useful, hopefully, in these states. And the nice property is that if you once ignore quantum corrections, the first order always gives you the correct classical function. So for any function of the basic operators, you get the same function in the basic variables. There's also small scaling with respect to P, which I do here. But this is, of course, always excluding the higher order corrections, and I always get back the classical theory. So this is not really very interesting because, like I said, we are not only interested to the discretization artifacts which happen because of discretization in the classical theory. We are really interested in quantum corrections. So can we go forward and somehow understand how these corrections of depending on the spread look like? It gets a bit messy maybe, but for me it's not so hard. So once again, I just write down what the basic action of these operators is. There's also not only the right invariant vector field, there's only something like the left invariant vector field on which our quantized functions in principle can depend. But we don't really need to care about the left invariant vector field because very early we found out there's an easy way to translate the expectation value on any left invariant vector field into a right invariant vector field. So this makes the situation much more nicer. And if you have, in principle, some polynomial operator here, which depends on multiple copies of the holonomies, there's also easy SU2 recoupling theory, which is standard known, in order to combine two of these SU2 elements to get only a linear sum over one SU2 element, which in other words means that we have the full control over our expectation value if we know the full expectation value, including the quantum corrections of one copy of a holonomy and many iterative copy actions of the right invariant vector field of the fluxes. Every polynomial operator you're interested in, you can build out of this building block, in other words. So this one is what we have to investigate. On each edge, of course, right? So I drop the label E for the edge at this point, but you have this on every edge. Bringing a bunch of edges together gives you an operator on the edges. But since this is a tensor product, these easily decouple. And there is indeed a general formula including the first order corrections in T, which is pretty nice. So it looks maybe a bit horrible because it's spanning several lines, but it's still very compact if you compare to other equations you have to work with in quantum gravity. So it's really a powerful tool, which is the expectation value, including the OT corrections, in the first order of these OT corrections for an arbitrary set of our basis elements. Like I said, combining all of them together, you can use it to evaluate any expectation value for polynomial operators in this cosmological kinematical configuration. So, of course, it would still be a lot of handiwork. If you look at this function for every edge, you get a lot of these functions, very hard. If the sum of them, we wrote a mathematical code to execute all of these tools automatically for us. So, how would this operator, this algorithm look like? It takes a polynomial operator you're interested in because you want to study it, as long as it builds out of holonomies, the right invariant fluxes, and for those experienced in AQG, also this operator Q, which is just PP, the determinant of P, which is important because we can then approximate the Ashkenazi-Lewandowski volumes by methods of Giesel and Tiemann. And also this operator can also involve commutators, because, for example, there's typical quantization of the scalar constraint will involve commutators. And you can compute all of this. You can, since we have been fairly general at the moment, not only use this for quantum gravity, but for all SU2 gauge theories you're interested in. But of course, in order to give you a possible application, I will talk about quantum gravity. And so one example, just to present it to you, if you take the Euclidean part as regularized by Tiemann, it looks like something like this. So it has commutators, it has polynomial behavior on the holonomies, and it has the volume, which is just a function of the fluxes if you approximate it by Giesel and Tiemann's polynomial. You can run this through our algorithm, you get easily the expectation value of the Euclidean part, including some quantum corrections. But what to do with this now? Now we have this algorithm, but how can we really use it? What can we do with it, which is useful? Well, there are several things you can do. First thing, of course, you could ignore these T corrections, right? Send T to 0, you get the classical result back, and you can say, okay, let's take the expectation value of my scalar constraint or some Hamiltonian I'm interested in, some observable, computed by the reduced Poisson bracket, which we have identified in the first part of the talk, dCdP, and say, like I said, eta relating to P, psi relating to C, you get a new dynamics, you get this effective behavior. Like I pointed out, Ashtika, Patwolsky, and Singh did this the first time for the sine term. Sanusi, Dabor, myself, and Bartowski did it also for this regularization of Tiemann, and a lot of people have since then adopted this effective behavior. But now we have these T corrections at hand, so we should use them as well and see what we can get from them. So the first thing we did when we computed this T corrections for the Euclidean part is that we found out that if you actually compute the Poisson bracket of the expectation values and compare this with doing the commutative of the quantum observables and then taking the expectation values, you don't get the same result. The T corrections are really different. And this deviation is really, really important because it can pile up and can really lead to a totally different effective outcome. So instead of a bounce, you might get several bounces. Other strange thing happens, as we investigated with this Euclidean part of the constraint. It's not the full constraint, right? But so we already have shown that if you include T corrections, the effective behavior really gets messed up, and you should not use this description if you would really like to understand how the quantum effects look like. A cool thing is that independently, shortly after us, there was also a second algorithm constructed, also with researchers here from Warsaw. And by using a supercomputing cluster, they were able to also get the Lorentzian part. So now they had access to the full theory, Euclidean and Lorentzian part, and they investigated also by these effective theories. And so what I really like about this work is that it confirmed once again that some of this effective theory breaks down, because in their model, if they would use this for an effective theory, they would not even get the correct late time dynamics. So there would be a recollapse happening for a flat isotropic cosmology, showcasing that the effective dynamics somehow has some problems. You could, of course, remedy this, sort of look like a power series expansion, right? So instead of looking only at the momentum, which is this one, and using for Hamilton's equation, you could compute O dot dot, O triple dot, O quadrat. So multiple iterations with the Hamiltonian scalar constraint in order to get this object, and then compute, well, the power series expansion. And if you could somehow prove that it converges, someone get maybe some intel here. But we want today, in the last 10 minutes that I have, I want to use the algorithm we have in a completely different way, a completely novel way, in order to investigate the dynamical properties of such a coherent state family. Recall, this is just a kinematical state. We don't know anything whether the state remains stable under evolution or not. But we can maybe find out a little bit about this in the following. And what I will do in order to do this is I will talk about the quantum speed limit. So just small intermezzo, because maybe not all of you have heard about the quantum speed limit yet. A quantum speed limit is arises if you rewrite Heisenberg's inequality. So if I give you some state psi, labeled by S, or many states psi s, you know that, oh shit, it should be an O. So you know that the variance of O and H and E is always bigger, the product of those bigger than the commutator of O and H. So if I use for the state O, okay, read O here, if I use a specific state which is a projector and use some manipulations, I get this equation 41. This is the quantum speed limit. Tells us that the variance of the Hamiltonian times time it takes to evolve the state is always bigger than this certain algebraic expression over here, which involves the overlap of the state epsilon and this family psi s. Why have people like this? So this is really a tool which is famous in other applications, not so much in quantum gravity so far. But if you would now use a very specific state for this epsilon, namely the first state of the psi family, and also assume that at some point psi tau, these two states are orthogonal to each other, this equation simplifies further, and you see that the time from state 0 to state tau must always be bigger than something divided by the variance of the Hamiltonian. So you get a minimal time it takes for your quantum system to evolve. This is really like a very powerful tool. It has led to a lot of applications in quantum information theory, in quantum optimal control, where you can sort of find out how long would it take me if I want to use a quantum gate and a quantum computer in order to evolve from one state of the qubit to another one, because there's a minimal bound it takes at least. This has been used in quantum batteries, where they can say, make sort of a reverse bound where they say how slowly or how fast can a quantum battery discharge. And today, I want to show you how this tool can be used for quantum gravity. So where were we last time when we left? We talked about coherent states, and I told you these coherent states are kinematic. So of course, I could take a lot of these states, right? I could somehow take a classical trajectory, parameterized by z, which is psi and eta, and I look at the whole family parameterized by the states. And I say, well, probably this is now my semiclassical trajectory. It's a lot of states behaving in a semiclassical trajectory, which could be the evolution of the leading order of the Hamiltonian in classical lattice GR. But this family, I know nothing about this relation of this family to the relation of the real quantum evolution, right? Where really the state is evolved, could disperse quickly, could not have anything to do with it. In the best case, of course, this family would be stable. Like for the harmonic oscillator, we know this family is stable and this would be an equal sign. But, should be somehow related in order for us to be useful as a stable set of proposal for stable family. So it should be our task to figure out, is a family stable? Can we somehow get a bit of information about this equation? And we will use the quantum speed limit. We will twist it again a bit in order to get this information. So like I said, so let's call our epsilon state this state psi, so the conjectured trajectory, and the state psi s, I will use the real-time evolution. Once again, of course, I know this is the quantum speed limit. There's this epsilon, there's this psi s. All right, now let me move all of this up here. Same thing. What we want to find out is we want to find out whether the real evolution and the conjectured evolution somehow agree. So whether the overlap between them is more or less 1. Well, if the overlap between them is 1, then the arcus cosine will approximately be 0. Now I can use some basic inequality to shuffle this one to the other side. So I know this, a tau, which we're interested, must always be bigger than this expression over here. So if you give me any proposal for a stable family, it can only be stable if this expression, if this check here is passed, this equality holds. If the state is not stable, then, well, for example, if this one here would be 1/2, this one must be much, much bigger than 0. Therefore, this would not be very stable. And now we can use our algorithm, because the things we have to evaluate here, like the dispersion of the constraint, this is something polynomial, it's a polynomial operator. If we have access to the constraint itself, we have access to the variance as well. And only because we have access to the quantum correction, this term is different from 0. So, for example, if you would just use the Euclidean part, you could compute this variance with our algorithm straightforward. You can get this expression. It looks not so nice. You can also compute A0, which is just the overlap between two states, which we know, and do this as well. Gives us another expression. Funnily enough, we find that the variance of the Euclidean Hamiltonian appears here as well. So if you plug both of these in, you see that this actually cancels out, and there remains only one expression, which is positive, which there's only one negative expression which remains. And you find that this thing on the left here, A0 minus the variance, is something which is always negative. So if this is always negative, this allows our A tau to be 0. Of course, it could be anything, but it can especially be 0. So the possibility that the quantum speed limit, that the state is stable, is there. So the quantum speed limit test is passed. That's the best thing you can happen with this test. You can really test, does it work? Do we get, does our proposal for a stable family really pass this test? If yes, awesome. We are still not sure. We need further investigation, but the first necessary consistency check is passed. So, like I said, you can of course now continue with this and do further things. But once again, because I'm running out of time, wrapping up, the quantum speed limit gives us a bound on a tight bound, actually, we can show this, on the evolution of a given quantum system. How quickly it can disperse, evolve. In quantum gravity, we reshuffle the quantum speed limit a bit in order to make it to a consistency check. A necessary consistency check that any proposal for a stable family needs to pass. If this state is not passed, for example, this right-hand side would not be 0, but bigger, the family is ruled out, cannot work as a semiclassical description. And really, this bound is easily violated. So you can cook up a lot of examples where it doesn't work. If you have, for example, 2 points in your trajectory, which limit t to 0 don't become the same, and if your variance is smaller than infinity, then you can immediately show this transition cannot be stable. You can also use the quantum speed limit in order for this Euclidean Hamiltonian, or we use this to show that if you have the limit of huge fluxes at t to 0, you can for any time find a small enough t such that the transition from z to this z tau is stable in such a way that the error between these is under your control. We think that this statement in particular can be generalized, but this is an ongoing work in progress, which will appear hopefully at some point in the future. Well, and that basically wraps up my talk. So, like I told you, while we're trying to work on the quantization of gravity, I think that always there are tools and methods which emerge, which in best cases are useful for other systems. I try to present today two more methods, which I hope can be also applied outside of quantum gravity. One is a symmetry restriction, a framework to determine whether it's possible to restrict to a simply reduced setting without loss of information. And it transpired that discrete quantum gravity has a cosmological sector. This mimics the effective behavior of LQC, mu not LQC. Second, we presented an algorithmic approach to expectation values, and including the OT corrections, the corrections of the spread, we could compute the expectation value of any polynomial operator. And we used this in order to develop the quantum speed limit, which is a consistency check that any proposal for a stable family of states needs to pass. And well, at least for the Euclidean scalar constraint, we could show that this proposal for the Euclidean state with the right parameterization trajectory passes this test. And that's why I hope that both of these tools might have further investigation when we try to investigate the semiclassical limit of quantum gravity. Thank you very much for your attention.
So thank you very much for the very nice talk. So now we have a few minutes for questions. So are there any questions?
Hi, can you explain again what is the quantum speed limit?
Sure. Maybe you want to be precise. So, like I said, the quantum speed limit in its original form, if you look at the literature, you might most likely find equation 42 as the minimal time it takes for your system to evolve from state psi naught to state psi tau. Right? In order to make this transition happen, at least this amount of time needs to pass. This is what the quantum speed limit is. But it is really a special case of this equation 41, which is just Heisenberg's equation rewritten. So we used it in order to get information over a tau, which is the overlap between, the state upside and the state psi s. Does this go into the direction which you wanted to hear, or is your question something different?
Thank you.
No, that's okay. So, and like that, what we did then, we rewrote this equation, which is the quantum speed limit, like I said, without a special case of restricting epsilon, psi naught, and then assuming these two are orthogonal. We said, no, let's don't do this assumption. We use instead two different states for this quantum speed limit. And then we get this equation here, which is our consistency check, which our family has to pass. If the overlap between the conjectured stable state and the real evolution is 1, then this must be 0. So in other words, this must be something negative. If this is not something negative, this can never be 0. The family can never be stable. So by computing this object on the right side, we have a consistency check for our proposal, or in general for any proposal of a theory for coherent states. You don't have to do this in quantum gravity. You can of course do this also for the anharmonic oscillator or something like this. Probably also for HUC, which we have not investigated yet.
so in some moment you told that some theory, this higher order, is violating this check. Yes, or
Yes. So the effective.
oh yes, exactly. So it's for the quantum cosmology. So how general this is? Do you think it's just always true, or? So can you say
Well, always I cannot say. I mean, there are certainly situations where it probably is not wrong, like the harmonic oscillator. It works very well, and also for AQC, it works really well, the effective theory, because we have checked the evolution of both of them. So there are cases in which it works. But as the system become more and more complicated and not just a one parameter quantization, we see that a lot of these problems occur. I mean, we have two investigations. One of us with the Euclidean part, we saw that it doesn't work. It gives some repeated bounces. You have the work by Zhang, Song, and Han, which also have this effect that in the late dynamics, you don't get classical GR back. So I think that this all indicates that somehow this effective theory in all general very often have some problems. Not always, but it's probably more likely to have problems than to work out.
Okay, thank you. So are there other questions? Okay, so if not, let's thank Klaus again, and maybe I will stop recording.